Hi, this is Dharani Murali and you are watching part 1 of Face Math series, in which we completed chapter 1 previous year board exam paper questions from the real numbers chapter in last video. So in this video we are going to start with chapter 2 polynomials. Let's start with the introduction. Since this is a very small chapter, we will complete this in one go. What polynomials are? Polynomials, we can call it as an expression or the sum of terms of the form kx power n, where k is any number and n should be a positive integer. N should be a positive integer and it should never be a negative integer, because if any variable gets a negative power, then the positive power or the positive exponent of the corresponding variable turns out to be in denominator. So the power of the variable of the expression should never be negative. This kind of terms in an expression is not considered as a polynomial. If this kind of term is present in any expression, then it is not a polynomial. So any polynomial is sum of terms of the form kx power n, where k is any number and n is a positive integer. Now coming to degree of polynomial, the highest power of the variable or say x in the expression is called as the degree of polynomial. Now polynomial is classified into various types based on its degree. So types of polynomial based on degree. If the degree is 1, that is, if the highest power of the variable present in the expression is 1, then it is called linear polynomial. And one such example is 2x plus 3. It can be anything. 2x plus 3, 3x plus 5, x plus 3, y plus 2, where y is the variable in the expression. So in that way, if the degree of the variable or the highest power of the variable in the expression is 1, then it is called linear polynomial. Now coming to degree 2, it is called quadratic polynomial, and generally we say the quadratic polynomial with the form ax square plus bx plus c, which is the general form of the quadratic polynomial. We can take any example like x square plus 5x plus 6, or 3x square plus 4x plus 2, or simply 5x square. Even if it is of a single term like 5x square, the degree of this expression is 2. Then it is called quadratic polynomial. Similarly, for degree 3, we call it as a cubic polynomial. So any expression of the form ax cube plus bx square plus cx plus d can be called as a cubic polynomial. This is one such example, x cube plus 12x square plus 48x plus 64. Now for degree 1 we say it as a linear polynomial, for degree 2 we call it as a quadratic polynomial, and for degree 3 we call it as a cubic polynomial. Now what if the degree is greater than 3? So in that case we generally call it as a degree n or nth degree polynomial, and we frame the general form as ax power n plus bx power n minus 1 plus cx power n minus 2 up to the last term k, which is a constant. So in this term, if we see, at every successive term the power of the variable reduces by 1. So this is the general form of the nth degree polynomial. So now let's see about the zeros of the polynomial. A real number k is said to be the zero of the polynomial p of x if p of k is equal to 0. So generally we represent the polynomials as p of x, that is the expression with the variable x. If a real number k is said to be the 0, then it should satisfy the polynomial p of x, that is we should get p of k as 0. Now we are going to see the geometrical meaning of the zeros of the polynomial. So we will see how it is represented graphically And while representing graphically, what is the shape that we are going to get for linear and quadratic polynomials? Now let's see for linear polynomial. Any linear polynomial can generally be represented as ax plus b, where a should not be equal to 0. Why a should not be equal to 0? Because if the coefficient of x here becomes 0, then this term will get eliminated and only constant will be remaining. Then this will no longer remain as a linear polynomial. So for every degree polynomial like linear, quadratic, cubic, the variable with the highest power or the degree of the polynomial should not have 0 as its coefficient, or in other words, its coefficient should not be 0. So now let's continue. For getting 0, that is p of x equal to 0, we are just equating the general form of this linear polynomial to 0, that is ax plus b equal to 0. We get x is equal to minus b by e. In this case, x equal to minus b by a is the only value where this polynomial will become 0. Or in other words, we can also say that p of x or this linear polynomials become 0 only for the value x equal to minus b by e. Coming to the graphical representation, if we take it as the coordinate, like we generally say y is equal to p of x. In that case, if for x equal to minus b by a, p of x equal to 0, then we can say that the y value is 0. Then we can take the coordinate minus b by a comma 0. If we plot this point on the graph, then it intersects the x-axis at only one point. So on representing this linear polynomial ax plus b on the graph, we will get a straight line, and this straight line will intersect the x-axis at only one point, so it has only 1, 0. This is what is about the graphical representation of the linear polynomial. Now let's see for a quadratic polynomial. The general form is ax square plus bx plus c, and here also this highest power x square should not have a coefficient as 0. So a is not equal to 0. Now taking this polynomial p of x to be 0, that is ax square plus bx plus c equal to 0, this is slightly different from that of this linear polynomial. That is, we will factorize this ax square plus bx plus c as x minus alpha into x minus beta, where alpha and beta are those values at which this polynomial will be 0, and x minus alpha and x minus beta are the factors of this quadratic polynomial. So we can say that at x equal to alpha, this polynomial p of x becomes 0, and also at x equal to beta, that is beta minus beta will be 0. It is clearly seen here. So at x equal to beta also, this polynomial p of x becomes 0. So we can say that alpha and beta are two such values at which this quadratic polynomial ax square plus bx plus c becomes 0. So we said that p of x is y, and if it becomes 0, then at x equal to alpha and x equal to beta, both the values, the y value is 0. So we get the coordinates alpha comma 0 and beta comma 0, which are the coordinates that intersect at x-axis at the values alpha and beta. Now coming to the graphical representation, if we represent this quadratic polynomial on the graph, we get a parabola, either upwards parabola or downwards parabola. This parabola would intersect the x-axis at 2 points. So the quadratic polynomial will have 2 zeros. Now coming to this 2 zeros of the quadratic polynomial, it has 3 cases, which now we will discuss. Now let's see the 3 cases regarding the roots of the quadratic polynomial. Coming to the first case, the polynomial or the quadratic polynomial has 2 distinct roots. So what does that mean? We have seen that the graph of the quadratic polynomial is upwards or downward parabola. When we plot it, we can see that the parabola intersects x-axis at exactly two distinct points, that is A and B. Either it is upwards or downwards parabola. There are 2 points A and B at which the parabola distinctly intersects. That is, the parabola intersects the x-axis at A and B, that is 2 points. So we can say that it has two distinct zeros. Now coming to the case 2, two zeros, that is repeated zeros, two same zeros. Okay, the same number will be repeated twice. Coming to the case 2, the quadratic polynomial has two repeated zeros, that is the same value is repeated twice. Now in this case, if we plot the graph, we can see that the parabola intersects the x-axis at only one point, that is A here. Either it is downwards or upward parabola. The parabola intersect x-axis only at one point. In this case, we say that since the parabola intersect x-axis at only one point, it contains two repeated zeros or two same zeros. In these two cases, that is in the first two cases, we can see that there are two real zeros for the quadratic polynomial. Now coming to the case 3, there are no zeros, or specifically we can say that there are no real zeros. So we can see that when we plot the graph in this case, the parabola does not intersect the x-axis at any point. Since it does not intersect the x-axis, it does not have any real zeros. So these are the three cases regarding the roots of the quadratic polynomial. With this concept, we can now start with the exercise 1, that is exercise 2.1. All this theory part, whichever we have discussed till now for the exercise 2.1 and whichever we will be discussing for exercise 2.2, I will post the pictures of this handwritten theory notes in Instagram, Facebook and Twitter. You can take it from there as per your convenience. Okay, now let's proceed with exercise 2.1. So now let's start exercise 2.1. In this exercise, there is only one question in which it is asked that we have to find the number of zeros in each of these graphs. Okay. So this red line represents the graphs given in the question. Now let's find how many zeros does these graphs contain. Okay. So for that, we should see that whether the graph intersects the x-axis or not. If it intersects, then we should find at how many points it intersects. Just now we have seen that a graph contains as many zeros as its intersection at the x-axis. Now let's proceed with the first subdivision. Here the graph given is a line parallel to the x-axis. So clearly we can see that this line does not intersect x-axis at any point. It does not intersect x-axis at any point. So we can say that it does not contain any zero, or we can say no zeros for this subdivision. Now let's proceed to the second subdivision. Here you see, we can see that here you see the graph intersects x-axis at this point. It intersects x-axis at only one point. So we can say that it contains 1 0. Now coming to the third subdivision, we can see that this graph intersects x-axis at this point, this one and also this. So we can see that 1, 2 and 3. In this third subdivision, the given graph intersects x-axis at 3 points. So it contains 3 zeros. Now let's see the fourth subdivision. It's clearly a parabola. It's an upward parabola and also it intersects x-axis at two distinct points. Now we have discussed, right, in the case 1, that is the parabola intersects x-axis at two distinct points. So it contains 2 zeros. Or specifically we can also say that it contains two distinct zeros. Now coming to the fifth subdivision, when we trace the graph, we can see that it intersects at 2 points in the negative x-axis and 2 points in the positive side of the x-axis. So totally intersects 4 times at the x-axis. So we can say that it contains 4 zeros. Coming to the sixth subdivision, we can see that the graph intersects here, and also here. So in the sixth subdivision, the graph intersects the x-axis at 3 points. So we can say it contains 3 zeros. So this is what is all about exercise 2.1. Now in the next theory part, we are going to see the relationship between the zeros of the polynomial and its coefficients. Now let's see relationship between the zeros and coefficients of the polynomial. So for a quadratic equation, ax square plus bx plus c, and obviously a not equal to 0. Let us take the two roots to be alpha and beta. Now if alpha and beta are zeros of this quadratic polynomial, then this quadratic equation or quadratic polynomial can be expressed as the product of its factors. So ax square plus bx plus c is equal to k into x minus alpha into x minus beta, where k is some constant. Now we will multiply these two factors. We will get x square minus alpha x minus beta x plus alpha beta. When we combine these two terms, we get k into x square minus alpha plus beta into x plus alpha beta. Now we will multiply k with these terms x square minus alpha plus beta into x and alpha beta. We get ax square plus bx plus c is equal to kx square minus k into alpha plus beta into x plus k alpha beta. Now by comparing the left hand side and right hand side of this equation, we can say that a is equal to k, and coming to b is equal to minus k into alpha plus beta. Now we know that k is equal to a, so for k here we are substituting a, and we will get minus b by a is equal to alpha plus beta. Now alpha and beta are roots of this quadratic polynomial. So alpha plus beta is sum of zeros of this quadratic polynomial. So we can say that the sum of the zeros of the quadratic polynomial is equal to minus b by a, that is negative of the coefficient of x by coefficient of x square. Now coming to c is equal to k alpha beta, and again we know that k is a. So we can put that c is equal to a alpha beta. On simplifying we get c by a is equal to alpha beta. And here also we know that alpha and beta are zeros of this polynomial. So alpha beta is product of the zeros, and c is the constant and a is coefficient of x square. So this equation we can say it as product of zeros is equal to constant divided by the coefficient of x square. So this is the relationship between the zeros and the coefficient of the polynomial, and this point we can use for solving the questions. That is, in upcoming exercise 2.2, in second question we can find that the sum and product of the zeros are given in the question, and we will be asked to find the quadratic equation or the quadratic expression actually. When sum and product of the zeros of a quadratic polynomial is given, then we can find the quadratic polynomial by x square minus whatever value is given for sum of the zeros, it can be substituted here, into x plus product of zeros. Or in other words, we can also say that x square minus b by a into x plus c by a, which we have obtained just now. And on little simplification, we will get ax square plus bx plus c. So with this, we are completing the theory part of this second exercise and also of this chapter. Now we will discuss exercise 2.2. Till then, if you are new to this channel and you are watching it for the first time, do subscribe this channel and click the bell icon so that you don't miss any notifications. Also follow me on Instagram, Facebook and Twitter so that you can get the handwritten notes of the theory part whichever we are discussing in our videos. Now let's get into the exercise 2.2. So in exercise 2.2, the first question reads that find the zeros of the following quadratic polynomials and verify the relationship between the zeros and the coefficients. So in the first part we have to find the zeros and then we will verify the relationship between zeros and the coefficients of the polynomial. Now the first subdivision, the given quadratic polynomial is x square minus 2x minus 8. Now to find the zeros, first we have to factorize this quadratic polynomial. Here we are using the method of splitting the middle term. How we will do that? We will see now. We will multiply the first and the last term. So by multiplying the x square and the constant term, we are getting here minus 8 x square. This term we are going to split in such a way that on multiplying we will get this term minus 8x square, and on adding these two terms we will get this middle term or the x term. So for doing this process, we will find the prime factors of this number 8. So 2 into 4 8 and 2 into 2 4 and s 2 into 1 2. 8 is equal to 2 into 2 into 2. So using these factors we can do the splitting the middle term process. Now you see, we can split it as minus 4x and 2x. If we add these two terms, we will get minus 2x, that is this middle term, and if we multiply minus 4x into 2x, we will get minus 8x squared. So in place of minus 2x, we can substitute minus 4x plus 2x. That is what we are doing here. X square minus 2x minus 8 is equal to x square minus 4x plus 2x minus 8. Now we can combine these two terms and these two terms. So in these two terms x is common. So when we take x out, we will get x minus 4, that is x into x, x square, x into minus 4, minus 4x. Now coming to the second half, in these two terms, 2 is the common factor. So 2 we are taking it out, and inside we will get x minus 4. 2 into x, 2x, 2 into minus 4, minus 8. These terms we are representing it as x into x minus 4 plus 2 into x minus 4. Here we have to note one thing. The term inside the bracket is same in both the halves. This is the format that we get whenever we perform the splitting the middle term for quadratic polynomial. The factor which we are getting inside the brackets should be same in both the halves of the expression. Now we can now consider these two terms. In these two terms, x minus 4 is common. So we are taking x minus 4 outside. Then we will get x plus 2. Now x square minus 2x minus 8. This quadratic polynomial has factors x minus 4 and x plus 2. These two are called factors. Now we will equate this quadratic polynomial to 0. That is, in turn we will equate each of the factors to 0. In this process we will find the zeros of this quadratic polynomial. So x square minus 2x minus 8 equal to 0, at x minus 4 equal to 0 and x plus 2 equal to 0. Now individually we will equate the factors to 0. When x minus 4 is equal to 0, we get x equal to 4, and when x plus 2 is equal to 0, we get x equal to minus 2. So 4 and minus 2 are the zeros of the quadratic polynomial x square minus 2x minus 8. Now finding the zeros is first part of this solution. Now coming to the second part, we have to verify the relationship between zeros and the coefficient of the polynomial. Now let's see. First let's take the sum of the zeros, that is alpha plus beta equal to minus b by a, where we have to verify that whether sum of the zeros is equal to the negative of coefficient of x by coefficient of x square. That we will check in the next step. So alpha plus beta, we will take the sum of the two zeros, minus 2 plus 4, we get 2. And for coefficient, this is of the format ax square plus bx plus c. So a is equal to 1, b is equal to minus 2 and c is equal to minus 8. This we will substitute here. Minus b, that is minus of minus 2 by 1, which we will get 2. So sum of the zeros is also equal to 2 and minus b by a is also equal to 2. So we can say that sum of the zeros is equal to minus b by a equal to 2. So one part we have verified for sum of the zeros, and the second part now we will solve for product of zeros. So for product of the zeros, the condition is alpha beta equal to c by a. Now we will find the product of zeros alpha beta equal to minus 2 into 4, that is minus 8, and for c by a we will take minus 8 by 1, that is also minus 8. Since these two values are equal, we can say that alpha beta equal to c by a equal to minus 8. So we have verified the relationship between zeros and the coefficient of the polynomial. Now let's move to the second subdivision of this question. Now in second subdivision, the quadratic polynomial given is 4s square minus 4s plus 1. So what we are going to do, we will multiply the s square term and the constant term. Here we see that the variable given is not x, it is s. So on multiplying 4s square and 1, we get 4s square. Now what we will do, we will split this term in such a way that on multiplying we will get this very term, and on addition we will get the middle term. So we can split 4s square as minus 2s and minus 2s, because minus 2s into minus 2s will give 4s square, and minus 2s plus minus 2s will give minus 4s. Now we will substitute minus 2s and minus 2s in place of minus 4s. See, 4s square minus 4s plus 1 is equal to 4s square minus 2s plus 1. Now we will combine these two halves and we will write it as 2s is common in this first half. So we will take 2s outside and we will write 2s into 2s minus 1. And in the second half we are taking out minus 1, so that we get 2s minus 1, which is same as that of this term. So in last term I said that the terms inside the brackets in this step should be same whenever we perform the splitting the middle term. So this term is common in both the halves, we will take it out, and the remaining terms we will keep as it is, that is 2s minus 1. Now you see we are proceeding with the same steps, that is 4s minus 4s plus 1 equal to 0 at 2s minus 1 equal to 0 and 2s minus 1 equal to 0. So we are equating these two factors to 0 to find the 0 of the polynomial. So when 2s minus 1 equal to 0, we get s is equal to 1 by 2. And again for the second factor, when 2s minus 1 equal to 0, we get s is equal to 1 by 2. Just now we have discussed three cases about the zeros of the quadratic polynomial, right? In second case we saw that two same roots are repeated roots. That is the case we are getting here. See, both the roots we are getting as 1 by 2, or both the zeros we are getting as 1 by 2, which is repeated roots. So the zeros of the polynomial 4s square minus 4s plus 1 are 1 by 2 and 1 by 2. This is the first half of the solution. Now we will prove the relationship. For sum of the zeros, we take alpha plus beta, that is 1 by 2 plus 1 by 2 in this case. On doing that, we get 1. And on taking minus b by a, here a is equal to 4, b is equal to minus 4 and c is equal to 1. Since it is of the form ax square plus bx plus c. So b is minus 4 and a is 4. We will take minus of minus 4 by 4, which is 4 by 4, which is equal to 1. So we get alpha plus beta equal to minus b by a is equal to 1. First case, for sum of zeros we have proved a relationship. Now proceeding to the product of the zeros, 1 by 2 into 1 by 2, that is alpha into beta, we are getting it as 1 by 4. And for c by a, c is equal to 1 and a is equal to 4. So for c by a we will get 1 by 4, which is equal to that of the alpha beta. So we will conclude by saying alpha beta is equal to c by a is equal to 1 by 4. Now let's proceed to the third subdivision. Now in third subdivision, the quadratic polynomial given is 6x square minus 3 minus 7x. The general form of the quadratic polynomial is ax square plus bx plus c. So, the powers of the variable should be in the decreasing order, like power 2, power 1, and here it is x power 0. Anything power 0 is equal to 1. So, we are not mentioning it here. Since it is not in the proper order, we are rearranging it and we will get 6x square minus 7x minus 3. Now, we are going to proceed with the splitting the middle term. 6x square into minus 3 we get minus 18x square. This minus 18x square we can split it as minus 9x plus 2x. So how we are doing it? We will prime factorize this 18. 2 into 9 18, 3 into 3 9 and 3 into 1 3. So we have factors 2, 3 and 3. Either we can write it as 9 into 2 or we can write it as 6 into 3 or we can also write it as 18 into 1. We can write 18 in 3 different ways, either as 9 into 2 or 6 into 3 or as 18 into 1. Okay, 18 into 1. So in these 3 combinations, we should pick one in such a way that on adding those 2 factors, we will get this middle term, that is minus 7x. So what we are taking, we will take minus 9x plus 2x. So that on multiplication we will get minus 18x square and on addition we get minus 7x. So we are substituting these terms in place of the middle term, that is minus 7x. 6x square minus 7x minus 3 is equal to 6x square minus 9x plus 2x minus 3. Now what we will do? We will combine the first 2 terms and the next 2 terms. We will take the common factor out and then we will combine the terms. In 6x square and 9x, we have 3x as the common term. So we take 3x outside and we get 2x minus 3. That is 3x into 2x will be 6x square and 3x into minus 3 will be minus 9x. Now for this term, we have already seen that the same term which is inside the bracket should be here. So we will take 1 as the common term because that is the only common term with which we can get 2x minus 3 inside the brackets. So now we get 6x square minus 7x minus 3 is equal to 2x minus 3 into 3x plus 1, which are the factors of this polynomial. Now what we will do, we will equate these 2 factors to 0 to find the zeros of this polynomial. So we take 2x minus 3 equal to 0, we get x equal to 3 by 2. And while equating 3x plus 1 to 0, we get x is equal to minus 1 by 3. These two are the zeros of this quadratic polynomial. So the zeros of the polynomial are 3 by 2 and minus 1 by 3. This is the first half of the solution. Now we will verify the relationship. That is sum of the zeros alpha plus beta, that is 3 by 2 plus minus 1 by 3. On taking LCM we will multiply this term by into 3 by 3 and this term we will multiply by 2 by 2. So 9 minus 2 will be 7, denominator will be 6. So sum of the zeros we get it as 7 by 6 and for finding minus b by a we will take it as, here in this particular term we get a as 6, b as minus 7 and c as minus 3. So for minus b by a, minus of minus 7 by 6, which is 7 by 6. So the sum of 0 is equal to minus b by a equal to 7 by 6. Now coming to the product of zeros, we multiply 3 by 2 and minus 1 by 3, which is minus 1 by 2, because we can cancel these 2 3's here. So we will get minus 1 by 2. Now coming to c by a, c is minus 3 and a is 6. So we can take it as minus 3 by 6, which is minus 1 by 2. So we get alpha beta is equal to c by a, which is equal to minus 1 by 2. So we verify the relationship between the zeros and coefficients of the polynomial. Now let's see the fourth subdivision. In fourth subdivision, the polynomial given is 4u square plus 8u. Here if you see, in the general form ax square plus bx plus c, only first two terms are present and the constant term is absent. In such cases, we can directly take the common factor out and we can find the factors in single step. Here if we see in 4u square and 8u, 4u is the common factor. So we take it outside, inside we will get u plus 2. That is 4u into u will be 4u square and 4u into 2 would be 8u. So for 4u square plus 8u equal to 0, at 4u equal to 0 and u plus 2 equal to 0. Here we will find the u values because the variable in the polynomial is u. When 4u equal to 0, we get the value u is equal to 0, and when u plus 2 equal to 0, we get u is equal to minus 2. So the zeros of this polynomial 4u square and 8u are 0 and minus 2. Now we have done half of the solution. We will verify the relationship between zeros and the coefficients now. While doing the sum of the zeros, we get 0 plus minus 2 equal to minus 2. And for minus b by a, here if you see, a is equal to 4, b is equal to 8 and c is equal to 0. For minus b by a, we will get minus 8 by 4. So we get minus 2, which is same as that of the sum of zeros. So we get alpha plus beta equal to minus b by a equal to minus 2. Now coming to the product of the zeros, 0 into minus 2 is 0. 0 into anything will be 0. And c by a, c term is not present here, so c is 0. So for c by a, we will get 0 by 4 is equal to 0. Thus, we will get alpha beta equal to c by a equal to 0. Now we have verified the required relationship also. Now let's move on to the fifth subdivision. In fifth subdivision, the polynomial given is t square minus 15. Here the second term or the t term, that is x term, is missing. So we can write this polynomial as t square minus 15 as t whole square minus root 15 whole square. Because t whole square will be t square and root 15 whole square will be 15. Root 15 square is 15. So this is of the form a square minus b square. So we can use the identity a square minus b square is equal to a minus b into a plus b. So here a is t and b is root 15. So we can write this as t square minus root 15 square as t minus root 15 into t plus root 15. So the factors of t square minus 15, the given polynomial are t minus root 15 and t plus root 15. Now we will equate these factors to 0 to find the zeros of this polynomial. While equating t minus root 15 to 0, we get t is equal to root 15, and while equating t plus root 15 to 0, we get t is equal to minus root 15. So here the zeros are of the same value and opposite signs. So the zeros of the polynomial t minus 15 are root 15 and minus root 15. Now we will verify the required relationship. Sum of the zeros alpha plus beta is root 15 plus minus root 15. While adding two values of opposite signs and the same value, we get 0. That is root 15 plus minus root 15 is 0. Now coming to minus b by a, here we get a is equal to 1, b is equal to 0 since the middle term is absent, and c is equal to minus 15. So minus b by a is minus 0 by 1, that is 0. So alpha plus beta equal to minus b by a is equal to 0. Now coming to product of the zeros, alpha into beta, root 15 into minus root 15. Root 15 into root 15 will be 15 and this minus will be retained here. So we get alpha beta as minus 15. Now coming to c by a, we know c is equal to minus 15 and a is equal to 1. So we will get minus 15 by 1 is equal to minus 15. Thus we verify the relationship of the product of the zeros, which is equal to c by a with the value minus 15. Now let's move on to the sixth subdivision. So in the sixth subdivision, the polynomial given is 3x square minus x minus 4. Here again we will multiply the x square term and the constant term, and we will proceed with the splitting the middle term method. So on multiplying 3x square and minus 4, we get minus 12x square. So this we are splitting it as minus 4x plus 3x. For 12 we can take it as 3 into 4 or 2 into 6 or 1 into 12. So in this combination we will get minus x. So we will split minus 12x square as minus 4x plus 3x, so that we will get minus x, that is the middle term of the polynomial. Now we will substitute these two terms for minus x. 3x square minus x minus 4 equal to 3x square plus 3x minus 4x minus 4. So in these two terms we have 3x as the common term, and in second half we have 4 as the common term. So we will take 3x outside, we will get x plus 1, 3x into x, 3x square, 3x into 1, 3x. And again here minus 4 into x, minus 4x, and minus 4 into plus 1, minus 4. So in these both halves, x plus 1 is the common factor which we are taking it out. So we will get 3x minus 4. So for the polynomial 3x square minus x minus 4, the factors are x plus 1 and 3x minus 4. Now what we will do? We will equate the factors to 0 to find the zeros of the polynomial. What we are doing? X plus 1 equal to 0. We will get x equal to minus 1, and while equating the second factor 3x minus 4 equal to 0, we will get x equal to 4 by 3. So the zeros of the polynomial 3x square minus x minus 4 are minus 1 and 4 by 3. Now we will verify the relationship, that is sum of the zeros alpha plus beta, that is minus 1 plus 4 by 3. Here we will take LCM. With this minus 1 we will multiply and divide by 3, so that we will get 4 minus 3, that is 1, and denominator will be 3. So alpha plus beta will be 1 by 3. Coming to minus b by a, here a is equal to 3, b is equal to minus 1, and c is equal to minus 4. So for minus b by a, it will be minus of minus 1 by 3, that is 1 by 3. So we get alpha plus beta equal to minus b by a equal to 1 by 3. Now coming to product of the zeros, we will multiply the zeros, that is minus 1 into 4 by 3. So we get minus 4 by 3. Coming to c by a, c is minus 4 and a is 3. So we will get minus 4 by 3. Thus we get the product of the zeros, that is alpha beta equal to c by a equal to minus 4 by 3. Thus we have proved the relationship between zeros and the coefficients of the polynomial. The first question of this exercise 2.2. Now let's move on to the second question. In second question it is given that find a quadratic polynomial each with the given numbers as sum and product of its zeros respectively. So the numbers given here are sum of the zeros and product of the zeros of the polynomial, and we have to find the quadratic polynomial. So while seeing the theory part, we have also seen that when sum and product of the zeros are given and quadratic polynomial is asked, we can use this step to find the quadratic polynomial. So in this we will substitute the sum of the zeros and product of the zeros, and on simplifying we will get the quadratic polynomial eventually. Okay. So here the sum of the zeros alpha plus beta is given as 1 by 4 and alpha beta is given as minus 1. So what we will do, we will substitute these two values in this value. So what we will do, we will substitute these two values in this step. Okay. So what we will do, x square minus 1 by 4 into x plus minus 1. We will remove the brackets and write it as x square minus 1 by 4x minus 1. What we will do now, here there is a denominator 4. So we are going to multiply 4 throughout this expression. Okay. So what we will get, 4x square minus x minus 4. So this is the quadratic polynomial required in this particular question. Okay. Now let's move on to the second question, where the sum of the zeros are given as root 2 and product of the zeros as 1 by 3. Now what we will do, we will substitute these values in this condition, like x square minus root 2 into x plus 1 by 3. We will remove the brackets and we will get x square minus root 2x plus root 2. X square minus root 2x plus 1 by 3. Here in denominator 3 is present. So to bring it to the proper form, that is ax square plus bx plus c, what we are doing, we will multiply this expression throughout by 3. So what we will get? 3x square minus 3 root 2x plus 1, and this is the required quadratic polynomial. Now let's see the third subdivision, where the sum of the zeros is given as 0 and product of the zeros is given as root 5. This we will substitute in this condition. So we will get x square minus 0 into x plus root 5. So directly here we are getting it as x square plus root 5, which is the required quadratic polynomial. Now let's move on to the next question. So now in this fourth subdivision, the sum of the zeros are given as 1 and product of the zeros is also given as 1. So what we will do? We will substitute these values in the condition x square minus sum of the zeros into x plus product of the zeros. So we get x square minus 1 into x plus 1. On simplification, we will get x square minus x plus 1. This is the required quadratic polynomial and solution of this question. Now coming to the fifth subdivision, the sum of the zeros are given as minus 1 by 4 and product of the zeros are given as 1 by 4. So what we will do? We will substitute these values here and here. So we will get x square minus of minus 1 by 4 into x plus 1 by 4, and while removing the brackets we get x square plus 1 by 4x, that is minus into minus plus. So plus 1 by 4x plus 1 by 4. Here we have a denominator value 4, which is same in both these cases. So what we will do? We will multiply throughout this expression by 4. On simplification we get 4x square plus x plus 1 as the final solution. Now coming to the last subdivision of this question, the sum of the zeros is given as 4 and product of the zeros is given as 1. Here, since both these numbers are whole numbers, there is not much simplification. We just have to substitute these values in the condition and we will get the answer. X square minus 4 into x plus 1. So we will get x square minus 4x plus 1 as the required quadratic polynomial. With this question, we are completing this chapter. For those who are using the previous edition book, the next exercise 2.3 is deleted. So with this question, with this exercise 2.2, we are completing the chapter polynomials. In next video, we will discuss the previous year asked Cbse board questions based on the second chapter polynomials, that is based on this chapter. Okay. So let's meet in the next video. Until then, bye bye.